Hello everyone, welcome back to the session of digital communication, and let me share my screen and continue with where we left in the last session a few minutes ago. Okay, I'm sharing my screen, just a moment. So essentially we'll try to finish our topics with up to quadrature amplitude modulation QAM, and with a brief summarization of all the carrier modulation techniques we have done so far. Okay, am I audible?
Yes, sir.
Okay. Let me take attendance also now itself. So before we reach till QAM, just a quick go through once again. So we started with the ASK, and I think we have done it with the same set of slides. So I'm not going to explain at least for ASK. And yeah, this was the frequency shift keying, where we had two frequencies, FC1 and FC2, and the output signal is either a sinusoid or cosine at FC1 or FC2 on the basis of whether you have a binary 0 or 1. So it is less susceptible to noise, your Fsk, because there are no amplitude variations, and if at all whatever noise interference will come, it will appear as a amplitude deviation that can be removed using the limiter circuit, voltage limiter or clipping circuit. So we can say that Fsk is a superposition of two ASKs at FC1 and FC2. So though the amplitude is constant, but it is again representing some constant value. So this is a ASK at FC1 and this is an ASK at FC2. Remember, Fsk is equivalent to superposition of two ASKs at FC1 and FC2. You all agree with this? Because if you go back and look at the ASK, what is ASK? ST is a C cos 2 pi FCT. Okay. So similarly, your Fsk, I'm not saying Fsk is ASK, it is superposition or combination of two ASKs, but at different frequencies. You all agree with this statement? Students?
Yes, sir.
Okay. And so it is generally used for a low speed modem kind of digital data transmission, and therefore it is inferred that there is one DT controlled switch or key switch which is responsible for shifting the frequency of the carrier from FC2 to FC1 and FC1 to FC2, or higher or lower, whatever representation you want. So it is known as frequency shift keying. This was the modulator which we seen. This is a balance modulator. You are using a carrier wave here as AC cos to FC1T. Here the another part is of AC cos 2 by FC2T. So the carrier frequency is taken separately. Modulator ASK, this is other ASK, and you are adding it that is resulting into your Fsk. And see, giving us if 1 there will be 0, so this will not generate.
So your voice is breaking.
When you now some network glitch. Hello.
Sir, your voice is breaking. Your voice is breaking, sir.
Should I do? Let me check the system. Now I've changed the network now.
Yes, sir, it is audible.
Okay. So I hope you didn't miss this superposition of 2sk part. Am I audible?
Yes, sir.
Okay. So Fsk we can see as superposition of two ASKs, but the difference is the frequency, of the carrier is different for the two ASKs, and that is what is there in the circuit. Okay, so you can see our data is coming here, and so it will be 1 0 1 0, some logic will be there. We are inverting this and feeding it to the another balance modulator, and directly we are feeding the input data to one balance modulator. So if one logic 1 comes here, bit 1 comes here, it directly goes to this part. The inverted of 1 is 0. 0 balance modulator, if you multiply, you will get 0. So by the time you are having a bit 1 here, this balance modulator will produce a substantial output, whereas at the same time this balance modulator will produce nothing, 0 contribution. So bit 1 comes, this BM is active. This, when 0 will come here, this balance modulator will be active. So when we say this balance modulator will be active during occurrence of a 1 here, the signal which you are getting generated is at FC1 frequency. When a bit 0 comes, you have this balance modulator, and the output will be FC2. The carrier frequency will be FC2. So 1 0 1 0 coming here, and you are getting FC1, FC2, FC1, FC2, etc. like that as your Fsk modulated signal. Okay, so this is just a brief brushing up first. Are we good, students? So we have seen the problem in BFSK was discontinuous phase. So we used a technique called continuous phase frequency shift keying. Okay, so how do we ensure that? So with CP Fsk, continuous phase Fsk, the carrier frequencies, these they are selected such that they are by an exact multiple of 1/2 of the bit rate, because the data bit is coming at a particular bit rate RB. So if we select FC1 and FC2 equal to integral multiple of RB by 2, okay, because we are separating in the two directions. So we will never have a phase discontinuity ever. And the modulation index for Fsk is given by this formula. This is a discontinuity showing in your phase. Okay, I hope this is clearly visible screen. Please can you respond?
Now it is, sir.
This slide was not visible.
BFSK one?
No, yeah, BFSK modulator. Yes.
Yes, it was, sir.
Okay. So this is your continuous phase where you have phase between bit transition is continuous. There is no abrupt change, as you can see here. And in discontinuous, you have discontinuity. So we achieve CPFSK with the help of just keeping our FC1 and FC2 integral multiple of 1/2 of the bit rate at which the data input is coming. Then you have Fsk Demodulator. So if you look at the non-coherent demodulation scheme, you have a 2 ASK demodulator. Like how we considered Fsk as superposition of 2 ASKs. Similarly, if you look at the Fsk demodulator, you consider a circuit having 2 ASK demodulators. So whatever input signal you will receive, that may be the signal at FC1, FC2, FC1, FC2 based on the value of the binary bit 1 or 0, 1 or 0. So same you are feeding to envelope detector. So as I promised, we will look into envelope detector and all those simple concepts after this topic today or maybe next week. Okay, so we are using an envelope detector, but before we feed, we are filtering it with the central frequency FC1 and FC2. So only if the signal, incoming signal, is having a component of FC1, only significant output will be there here, which is acting as an input to this envelope detector. By the time you have a FC1 component, nothing will be there as the output of this BPF, because its central, the cutoff frequency is, central frequency is FC2. Okay. Similarly, you are sampling it, both these outputs at a particular rate, and then you are comparing it with some comparator and deciding what bit value is there. Okay, whether it is a 1 or a 0. So for continuous phase FSK, if you are going for a CPFSK, you can use phase locked loop in similar manner if you have done in your FM demodulation. So we'll see later on. But is this scheme, simple scheme, clear to you? Using 2 ASK demodulator to generate your to demodulate your FSK signal. Everyone? Okay, I believe it is. Okay, so we have seen Fsk bandwidth and power spectral density. So bandwidth requirement is like this. So you have a FC1 and FC2, and RB is your bit rate. So FC2, how much you are going ahead, plus RB. Here FC1, if you look at this lower side, it is again FC1 minus the bit rate, that is RB. So essentially it is FC minus RB, FC1 minus RB till FC2 plus RB. So this is the bandwidth requirement, that is FC2 minus FC1 plus twice of RB. So this one becomes FC2 minus FC1 plus RB plus RB. So plus 2RB, that will be the bandwidth requirement. So higher bandwidth is required in comparison to ASK. Higher power also is required because you have two peaks at different frequencies. But it is this BPSK we have seen in very much detail. Just you can go through it. I will share this, and we are using balance modulator to generate a BPSK. This inside of balance modulator we have seen with the help of balance ring modulator, and this is the bandwidth and power spectral density for binary phase shift keying. So by this time BPSK should be very much clear to you. So when you look at the power spectral density of BPSK, here it's only, this is BPSK, okay, not BFSK, PSD of BPSK. That BPSK does not have an impulse at the carrier frequency. So this is the, do you all know the significance of negative frequency? Minus FC. What is minus FC? Have you ever questioned? When you are drawing power spectral density, one side is the positive frequency, another side is the negative frequency. What is the significance of negative frequency? Does it really exist?
It is more of a theoretical thing that exists. In real life, I don't think it matters.
Yes, very good answer. It is exactly what said. It is just for mathematical representation because the theory we are using to analyze gives us negative frequency values also. That's fine. There is nothing like a negative frequency concept. All we are focusing on is positive frequency value. So good answer. Okay, so the bandwidth requirement for your Dpsk is twice of Rp because there is no impulse at the carrier frequency. Then Psk Demodulator, we have seen this today itself. We have seen this is, I think, a kind of shorter version of the what we have seen today. There is another differential Psk, Dpsk. So as the name suggests, earlier we have seen differential word. So differential is with reference to the past bit. So differential Psk deals with the signal transition from 0 to 1 and from 1 to 0. How it looks like? In Dpsk, the phase shift is with reference to the previous bit. So differential means it will be always with the reference to the previous bit transmitted rather than to some constant reference signal. If the incoming bit is 0, the signal phase stays the same as previous bit. If the incoming bit is 1 present, so the phase switch will happen. The phase will change. Needs differential data encoding before Psk modulation. So Psk modulation, use of balance modulator. So before you use a balance modulator, you need a differential data encoding. What is that? So you can see this is 0 and next bit is 0. If incoming bit is 0, the signal phase stays the same. So this was the phase, so it was continued. No phase change occurred. Compare it with the Bpsk. If you remember, bit 0 means phase 180 degree, but here in Dpsk it will continue. When a bit 1 comes, it will be just the reverse of the phase of the previous bit. So 0, it was continuing like this, and suddenly bit 1 has come, so the phase has to reverse like this. Like this. Now again 1 has come, so the phase will be the reverse of the previous. So previous, again it is reversed, and this is continuing at this time interval. The next bit time period when it starts, what is the bit? 0. So the phase will continue how it was earlier, like this. Now again bit 1 has come. So I hope you see the difference between the Dpsk and Bpsk. Are we good on this? You understood this this plot? Everyone? बोलिए please.
Understood, sir.
है ना? So if I will show you two means signal plots like this, and indicating that one is Dpsk, one is Bpsk, would you people be able to write the original bit pattern? Yes or no? So I will consider silence as yes. Okay, so I believe you all would be able to perform it. Given a signal plot like this, you can depict the bit pattern given you have provided the information whether it is Dpsk or Bpsk. Okay. So how do you ensure this differential encoding? This is the circuit for differential encoding, the Dpsk modulator. Okay. So as we said, before balance modulator occurs, you do line encoding, differential encoding, differential data, and not line encoding, differential data encoding. So you use a XOR bit, and you also use a delay circuit. So you can see the input binary data is represented here as empty. This is XOR gate. This is some output is coming, say DT, the current output. Okay, is DT, you are giving 1 bit delay. So 1 bit means bit duration. So bit duration is how much? TB. So this date output of this delay circuit will be, input is DT, it is waiting you for TB. So the output is DT minus TB. There will be delay in time domain. This is going as the another input to the XOR gate. So this is a differential encoding. So if empty is the message, the differentially encoded output DT you obtain with the help of this circuit. 1 to represent transition in given data sequence with respect to previously encoded bit. 0 means no transition. That's what we have seen in the definition of Dpsk. 0 means signal phase stays the same. Incoming bit is 1, so phase switches. So we start like this. This is your empty incoming bit. Let assume you have a dt minus tb as of now is 0. Okay, this 0, and you obtain empty as also 0. So XOR 0 0. What will be the dt? Next input to this is 0 0. Output will be XOR. Please students, if XOR input is 0 0, output is
0.
0. So if let me write it. So if this is 0 and 0, output will be 0. Okay. Now this dt 0, and this is waited for tb time period. This becomes dt minus tb, means this dt now will take the value of dt minus tb in the next instant. Next instant will come after tb time duration. Okay, and hence you can see this dt is becoming, so this current value is becoming input in the future like this as dt minus tb. Okay, so this 0 I am representing here. Empty is 0, then XOR operation of 0 0 again will be 0. This goes like this, same. Okay, now our data is changed. Now you can see 1 has come. When 1 has come, 0 and 1, this XOR operation will lead you 1. I hope you are able to see this. 1 and 0 is 1. XOR input 1 and 0, or 0 or 1. 0 1 1 0, both outputs are 0 for XOR gates. So based on your input bit pattern, whatever 0 or 1 it is coming, you are getting output dt. So when 1 came, you have 1, but when your 0 came, still the dt was 1 1. Suddenly bit 1 came, so according to definition the phase has to switch, so this previous 1 becomes 0. Again 1 comes, so this 0 has to become 1. 0 came, no change, so it stays at 1. Again 0 comes, it stays at 1. Is this clear to everyone? This small table is very important. If you have any small doubt, please ask me. No doubt? Arpit Patel, can you listen? Dev Satpara. Bhavya Soni. Ananya Khandelwal. Anshu Prajapati. You all can listen. Prachi. Nachiket.
Yes, sir.
Is it clear, this Dpsk?
Yeah, it is a little bit unclear, sir.
Okay, so tell me where it is unclear.
Uh, yeah, sir, the encoder portion of it only, sir.
Okay, so Nachiket, to understand this, just recollect the definition of Dpsk. What is the definition of Dpsk? Says if your incoming bit is 0, means at present you are receiving a bit 0 in your data stream, signal has to be same phase. I mean the signal phase has to stay same what was earlier. Means the output will continue with whatever value it was just before a 0 came. Okay.
Okay.
And if the incoming bit is 1, we are receiving now 1, and we have to do something. We have to modulate it, right? We have to modulate the carrier. So when bit 1 comes, whatever was the previous output just before incoming of bit 1, we will change the phase. So the value will change. So
And the value will stay that for one cycle.
yes, for one cycle, for one bit duration.
Okay.
If you are receiving 0, just don't do anything. Let the previous output go away. If you receive a bit 1, you have to reverse the phase. If it was 1 earlier, make it 0. If it was 0 earlier, make it 1. But when you have to do this? Only when you are receiving a 1. So that is what this circuit is doing. What you are receiving is represented by empty. You can see here, you are receiving empty. And on the basis of this reception of empty, you have to produce an output dt, this one.
Okay.
So what is the rule? Dt will change its value whenever empty will come 1. When empty will come 0, let it be the previous dt what was there. Don't change it. So let's start. This red color means let us assume we had dt minus tb as 0 at this point. So whatever it is, empty was 0. So whether I will produce a change in output? No. My dt will be exactly what was earlier, dt minus tb. dt से पहले क्या था? dt minus tb. और हमको क्या मिला इनपुट में? 0. I will not change. My dt will be 0. Next time period, bit duration, I again got 0. So what should I do according to definition? Please continue with whatever you had earlier. Earlier what was there? 0. So still it will be 0. Now a bit 1 has come, and according to definition, my dt, which was earlier 0, now has to change to 1. Okay. Now dt has come 1. Now next bit, input bit is 0. According to definition, nothing you have to do, just pass on the same 1, same bit. अगर यहाँ पे 0 होता तो 0 आता, अभी यहाँ पे क्या है? 1. So our output will be 1. Again a bit 1 has come, so we will do nothing. I mean our circuit will do nothing. It will not change the previous state. The state it is 1. Here you notice now bit 1 has come. So according to definition, whenever bit 1 comes, phase has to change. What was the earlier output? Please change, reverse the phase. So 1 becomes 0. Got it?
Yes, sir.
Now you have got 0. Again, next bit which is incoming is 1. So according to definition, phase has to reverse. So now you have 0, you have to do it. You have to reverse it. So now it becomes 1. Now next bit which is incoming is 0. Do nothing. 1 was there, just 1 will be there. Again bit is 0 is incoming. It will stay the same 1. I hope now it is clear. Yes, Achiket?
Yes, sir. Yes, sir.
And to all students, please, proactively you should ask. So it is easily implemented. This differential Psk is easily implemented by modulo 2 arithmetic. So XOR gate in arithmetic it is known as modulo 2 arithmetic. And dt we are representing empty XOR operation dt minus tb. So once you get your differentially encoded data dt, all you require is now to just perform a Bpsk. And in Bpsk, input has to be bipolar in nature. So you need a bipolar conversion. By this time, dt is unipolar. Convert it to bipolar, feed it to a balanced modulator. Another input will be a carrier cos omega ct, and output will be a Bpsk. But only the difference is directly input you are not providing, but rather you are converting it into a differential coded form. I hope this is clear to everyone. If you have any doubt, please ask. And rest of this is whatever is there is history for you. You know everything. Balanced modulator inside you have seen, so you are should be pretty much clear with the generation of a different phases in the output of a Bpsk. So shall we move forward? Students?
Yes, sir.
Okay. So this is the Dpsk Demodulator, and similar in the reverse manner. First you will need a band pass filter, and then we are doing the reverse. So you are sampling the signal, providing a delay of dB, and then feeding it to balanced modulator, and then performing a low pass filtering. You will get the output. Okay, so this is the Qpsk Demodulator. So you can go through it. We have seen M-array Psk or multi-level Psk. So we select number of phases as 2 to the power n, and we are keeping number of bits which we are considering. So if n was 1, it was Bpsk. If n was 2, it was Qpsk. We have seen this is very detailed. If you are selecting n equal to 3, you will have how many phasors? You will have 8 phases. Okay, and we call it as 8 Psk. So in 8 Psk, we are grouping 3 bits. So essentially, if you consider a M-array Psk, M-array means M number of phases are there in that phase shift keying scheme. So the successive phase angles will differ always by 2 pi by m. Okay. So this is the thing, and the bandwidth requirement, it is dependent on how many, what is the value of m and n. So Qpsk we've seen in detail like this. These die bits we have seen, the bit splitter was doing what? Separating D0 and D1. This is I channel, this is Q channel. Okay, and then considering the values before the cos and the sine, either as +1 or -1, we had different phases in the Qpsk. So whenever I will share this PDF, don't get confused in what I taught you. I taught you 1 0 here and 0 1 here. Remember, this is value of IQ here, in what I discussed you in the last session, it was Qi. So don't get confused. Hai na? You will find, you may feel that it is contradictory, but it is not. It is IQ, I0, Q1, I1, Q0. But what we discussed earlier, it was the truth table was Qi. Hai na? Don't get confused. And this is the output, different phases, the same thing, okay? And how the signal will look like. This is Qpsk modulator, again a simpler version of what we discussed. You have serial to parallel converter, essentially bit splitter, and then you are feeding into different balance modulators. One of the input is cos and sine, and then you are linearly summing up and you are getting Qpsk. Okay, this is a Qpsk demodulator. Similar reverse fashion, you use band pass filter and then use of LPF and then decision circuit, and then performing parallel to serial conversion. There is something we call as minimum shift keying or MSK. So as we have seen, there are 4 phases in quadrature phase shift keying, and there are discontinuities in that. We have seen that sometimes plus 135, then suddenly plus 45, suddenly minus 45, then minus 135. So there are a lot of phase discontinuities in Qpsk. It is suffering from phase discontinuity. So to avoid discontinuity in the phase of Qpsk, we need a continuous phase modulation scheme, and that is nothing but we are calling as minimum shift keying. So like we had Fsk and CPFsk. Fsk, simple Fsk is having discontinuous phases. Continuous phase Fsk we were calling as continuous phase Fsk. In Fsk, just remember how we ensured a continuous phase. We made the selection of Fc1 and Fc2 there, integral multiple of half of the bit rate, if you remember, okay, NRB by 2. Similar fashion, MSK, which you are saying that continuous phase Qpsk, it is again with certain criteria. What is that criteria? Let's look at it. So MSK can be viewed as a special case of continuous phase Fsk, which is expressed as this formula. St is AK cos and cos minus B sin and sin. This formula, it looks like complex, not confused. F naught is your carrier frequency and dk is your plus minus 1. Depend the bipolar data. Phase constant. Hello, am I audible? Students, am I audible?
Yes, sir.
So what are those conditions? The frequency selection for the transmission is the center frequency plus 1 by 4t and f0 minus 1 upon 4t. These are conditions which you follow for a continuous phase Qpsk. You are calling it as MSK, just like how we had in continuous phase Fsk. Now this is important. Further improvement in transmission bandwidth using M-ARRI techniques. So you have seen ASK, FSK or PSK, they can be further refined. You can use M number of phases. They can be refined and calling as M-ARRI to send more than one bit at a time. And we have seen that in Qpsk. And how many bits we were considering? 2 bits. So we had 4 phases. Similarly, you can select number of bits. You can increase this number of bits to generate more number of phases so that more bandwidth utilization can be there. And this all is happening in the same time period, right? So this technique of having inclusion of multiple bits to generate more number of phases, there is a limit to it. You can go up till 5 bits. and beyond that you will get error. So if you are selecting 8 phases, 8 Psk, or if you are selecting 4 bits or means 16 Psk, we are calling the nomenclature as like this. Okay. The same approach you can use for amplitude and frequency shift keying. In practice, the maximum number of bits we can send is up to 5 bits. Now, what is the path remaining? So, for further improvement, if you further want bandwidth improvement, utilization improvement, only solution remaining is please combine different modulation techniques, ASK, FSK, PSK, how you can combine them together. So, that is nothing but QAM, Quadrature Amplitude Modulation. So it is a combination of MRE-PSK with ASK. Why we are doing this MRE-PSK mixed with ASK? For better bandwidth utilization, so that we can send more number of bits in the given time period. Just understand what is the purpose of going for QAM. We want better bandwidth utilization. How bandwidth utilization can be better? If you are able to send more number of bits in a given specific time period, right? So you, and just now we have seen we have to do something, we have to mix different modulation techniques. So we have decided to mix MRE-PSK with ASK. MRE-PSK, you are aware, M means number of phases. It can be 2, it can be 4, it can be 8, it can be 16. So quadrature amplitude modulation involves splitting the signal into different phases. Not only different phases, but also each phase with different amplitudes. Okay. So if in Qpsk we use 2 different amplitudes for each phase modulated carrier, then it results into 8 different combinations. By definition, Qpsk has 4 phases. Yes or no? Please, students, can you listen? Chirag, can you listen? Please, someone has to respond. Nachiket?
Yes, sir.
Am I audible properly?
Yes, sir.
Okay. I understand today is a heavy information flow for digital communication, but again, we'll finish at this QAM. We'll take it in much detail in next week. Don't worry, but just understand QAM is combination of 2 modulation techniques, digital carrier modulation. One is MRE-PSK, one is ASK. Okay, so Qpsk, how many phases are there? 4 phases, means 4 combinations of the phases you are having. So in Qpsk we use 2 different amplitudes for each phase modulated carrier. So we had 4 phases combination, but if we use 2 amplitude for those 4 phases, so total we have choices of 8 different combinations. So we call it as a 8 QAM. So when we have this 8 choices, how many bits we can code? 3 bits. So different variety of forms of QAM, they are available. 16 QAM, 13 QAM, 64, like that. Okay. This is the circuit. I think we'll do in next lecture. If you have any query, student, please ask, or else we are good to finish this session. Devang, can you listen? Devang Dave? So please, everyone, revise immediately on the same day, and it will be there in your mind for a longer time period. Okay. because with time now we forget the discussions. Okay, if no queries there, thank you everyone.